Hello class, welcome to Geometry Lesson 7-1, which is all about dilations. By the end of this lesson, you should be able to dilate figures and identify characteristics of dilations. So before I move on to the next slide, let's quickly remember what a dilation is. We've talked about this in past years, and a dilation, you may recognize the word dilate if you've been to the eye doctor. It means to either enlarge or make something smaller, while still staying like the same shape, same proportions. So in an example one, we're going to practice dilating a figure. So how do you draw a dilated image? Well, the method that I'm going to teach you is the ratio method. On your test and on your homework, you're going to have to draw a dilated image. And in the past, this has been the easiest method for students. If you're like, this just doesn't make sense to me and you want me to show you another way, I can show you that in class. But what you can do is measure from the center of dilation. That's always going to be your point. Kind of like back in, was that chapter 3, you had the center of rotation. We always had that dot that we would rotate around. Center of dilation is kind of the same idea. It's the point that we are going to use to connect to our line. So point P is our center of dilation. So if I wanted to dilate triangle ABC, I would start by laying my ruler so it lines up with point P and point A, and I would want to measure the distance from point P to point A. Then I want to look at my scale factor. In this case, my scale factor was listed up here, and it says 1/2. So if A was 2 inches away, let's say, now A prime would only be 1 inch away because it's half of the distance. So along that same line, I would then put a dot at 1 inch, and I would label it A prime. Next, I would take my ruler and I would line it up going through point B. I would say, how far is point B? Multiplied by 1/2, or for those of you that prefer, divide by 2. It's the same thing. And then I'm going to measure along that same line that distance that I just calculated, put a dot and label it point B, or actually B prime. And then you do the same thing for C prime, and then your very last step is to connect those dots. Okay, so kind of 3 steps. Step 1, lay the ruler so it goes through the center of dilation, in this case point P, and one of the vertices on the shape you are dilating. Measure it, multiply by the scale factor, and then put your new point wherever that measure would be. Okay. Last step that people tend to forget, just like with rotations, is people sometimes forget to connect the dots to remake the shape. So don't forget to connect your, in this case, A prime, B prime, and C prime. Oops. All right. So example 2, what if instead of me asking you to, whoa, that was weird, but kind of cool. How about instead of me asking you to perform a dilation, I ask you to analyze a dilation. So here, if we look, we have 2 rectangles, and which one is my original? My original would be the black rectangle because it's just A, B, C, and D. Remember, if there's A prime, B prime, C prime, and D prime, that prime tells us, that little tick mark is called prime if you've forgotten, that little tick mark tells us that that has been moved, that shape has been modified. Okay, so if we compare these 2 rectangles, can we figure out if this figure has been dilated? So in order to know that this figure has been dilated, I need to make sure all the angles are congruent. So if I look, okay, angle A is made by a vertical line and a horizontal line. That means that's a 90-degree angle. And same with the A prime. it's a vertical angle and a horizontal, or vertical side and a horizontal side. And the same thing holds true for all of the angles. You see how they're formed by horizontal and vertical lines? That means all of them are 90-degree angles. So that means all of the angles are congruent, so that's good. Next, we have to compare the side lengths and see, okay, our side lengths are not congruent, but we want to figure out, are they similar? And so similar means that all of the side lengths have the same proportion. So if I look, AB, if I count, is 1, 2, 3. So AB equals 3. And if I compare A prime, B prime, if I count that, get 9. Okay, so I would have, it was 3, now it's 9. Then if I look at BC, I see, okay, it was 2, and now it is 6. Same with CD, it was 3, now it's 9. And AD was, or DA, if you're just going around the rectangle, DA was 2, and D prime, A prime is now 6. So you see, if I take my image, okay, so remember the image is the one that has been changed, and put that on top, so A prime, B prime equals 9. And then I put my original on the bottom, AB, which was 3. And I say 9 divided by 3, I end up at 3. And CD was the exact same. It got 3. And then if I look at my other sides, I had 6 divided by 2 and 6 divided by 2, which also equals 3. So since all of these ratios equal 3, that means that these sides are proportional, which means the two figures are similar. So if I asked you, if I gave you this problem, okay, how are the side lengths and angle measures of ABCD related to those of A prime, B prime, C prime, and D prime? You would have to say, okay, the ratios are equal, and if you want to say they equal 3, perfect. So the lengths of the corresponding sides of the two figures are proportional. If you want to say the ratios are equal, so the side lengths are proportional, I'm okay with that. So I want you to look at this question on your own and figure out how are the side lengths and angle measures of the two figures related. If they are similar, like in the last one, I want you to tell me what that ratio was that you got. Good luck. All right, hopefully for this one you looked at the two rectangles and saw, okay, all of the angles are made by vertical and horizontal lines. That means the angles are congruent. And then you compared the side lengths and you said, okay, going from the original black rectangle to the image, the red rectangle, the proportion would be 1/3. If you're ever questioning, how do I know if it's 1/3 or 3/1? Remember, if you have an image getting bigger, it has to be greater than 1. If you have an original figure that's getting bigger in the image, your scale factor is greater than 1. If you go from big to small, then your scale factor has to be less than 1. Okay? That's one way to remember. If you're getting smaller, your ratio or scale factor is going to be less than 1. Okay, so then let's talk about example 3 and finding a scale factor here. So I've already used the word scale factor because I know you guys have used it in the past couple of years. So scale factor is the ratio of side lengths in the image to the corresponding side lengths in the pre-image. So I said original and pre-image are the same thing. But I have two side lengths. KL started as 12 units long, and my image ended up with 18 units. So if I wanted to figure out the scale factor, I would take the 18 and put it over the original, which was 12, and I would reduce that, and I would say 3/2. Do not write your scale factors as a decimal. I don't want that. I want an improper fraction, okay? Question 3, I want you to try to find the scale factor. So This is a two-part question. You can type it all into one answer when the video pauses to have you do that. First, look at this image, or look at this dilation, and figure out, is it an enlargement or a reduction? Is the original getting larger or smaller? And then I want you to figure out the scale factor. Good luck. Hopefully you looked at this and you said, okay, my picture is getting smaller because I have to go from ABC to A prime, B prime, C prime. And the scale factor, if I look, okay, AB was 2. That was a weird line. AB was 2. Now it's 1. AC was 1, 2, 3, 4. And now it's 2. Okay, so I can see that things are getting cut in half, right? So my scale factor is going to be 1 over 2. Example 4, let's practice dilating a figure that's in the coordinate plane with the center of dilation at the origin. Okay, we're going to do 2 types of dilations on the coordinate plane, one with it centered at the origin and one with it not centered at the origin. So first, let's talk about some of the notation you're going to see. So if I'm asking you to do a dilation, this is kind of what you would see. That D represents the word dilation, just like in chapter 3, we would do this, and I would say a reflection over the y-axis, or a translation of -5, 2. Okay, so we use a large letter and then a number or a word or phrase. Okay, so D stands for dilation. Okay, so dilation D3 means that the scale factor is 3. The little number represents whatever the scale factor is. So it's possible to also have a fraction there, because sometimes our scale factors are fractions. Okay, so dilation with a scale factor of 3 for triangle ABC. And if it is written in this notation, that also means that it is centered at the origin. I will show you what a non-centered at the origin one looks like as well, but that'll be the next example. So this is what it would look like for centering at the origin. Now, you guys are probably going to like this because this is pretty straightforward. So you start with your original points, and then if our scale factor is 3, you simply multiply all of your numbers by 3. So 3 times 2 becomes 6. 3 times the -1 becomes a -3. And then for B prime, -1 times 3 gives me a -3. 2 times 3 gives me a 6. And then 3 times 3 gives me 9. And 0 times 3 gives me 0. Then I just have to plot those points, and I am done. Sometimes I don't even ask you to plot the points. I just ask you to list the new coordinates. Make sure when you're listing those new coordinates, you don't say A is at 6, -3. You say A prime and B prime and C prime. If you forget those primes, your answer is incorrect, okay? So why don't you try to figure out what are the vertices of a dilation with scale factor of 1/4 of triangle PQR. Good luck. Hopefully these were the original points that you got for P, Q, and R, and then you just multiplied each of those numbers by 1/4 and ended up with P prime at 2, 1, Q prime at 3, -1, and R prime at -1, 0. If you have questions, please be sure to reach out for help. And now let's talk about the last example, which is when we do that same idea, except this time it is not centered at the origin. So you can see our notation changed a little bit. Now we have the scale factor, which is 1/2, but we have a comma R. So that R is a point on my rectangle QRST, and point R is now the center that I am dilating around, okay? So that means all of the points on this graph are going to be redone in relation to point R. So the dilation is centered at R, which is at negative 2.7, with a scale factor of 1/2. So if we think about it, that means every image point, so our new point, is half the distance from R as the starting point. So with a rectangle and the fact that it's not slanted or anything, this can be fairly simple. I'm going to show you the method that works for every figure, whether or not it's necessarily drawn as nicely. So the first step is to write down the pre-image points. Since this is a rectangle and one of our points is already the point of dilation, you don't have to include that. So you see I took point R out, and the first thing you're going to do is figure out the horizontal and vertical distances from point R. So if we compare Q, I don't have to move left or right in order to line up with point R. So I put a 0. Vertically, they are 8 units away from each other. And since Q is below, I'm going to do -8. And I do that for each of the points. I count how far is S away. Well, it's 6 to the right, but 0 up and down. And then point T is 6 to the right and 8 down. So you fill that in. You just start by figuring out the horizontal and vertical distances away. Then you take all of those numbers and you multiply by 1/2 because that's our scale factor, right? So 0 times 1/2 is 0. -8 times 1/2 is -4. Then I move on to point S. 6 times 1/2 is 3. 0 times 1/2 is 0. Point T. 6 times 1/2 is 3. -8 times 1/2 is -4. So that's how I got all of these numbers. Now, the last step is you add that information to point R. So point R was at -2.7, so you can see that's already filled in there. And then I took these numbers and plugged them in. So -2 plus 0 is -2. 7 minus 4 is 3. So that's how I found where Q prime should be. So -2, 3 would be right there. So that's Q prime. And then S, I'm going to add those numbers to -2 and 7. So -2 plus 3 is 1. 7 plus 0 is 7. So I'm going to go to 1, 7. And oh, sorry, that was 6. 1, 7. And then the last one you do that same thing for point T. You say -2 plus 3, and then you say 7 plus a -4, or 7 minus 4, and you end up at 1, 3. And this is T prime. So then my new rectangle is that right there. And then I would have to write R prime as well, because that's still part of the rectangle. Okay? So you can see, here's a nicer graph. If I asked you what the vertices are, because a lot of times I'm not going to give you the graph for these actually. I'm just going to give you the points and say, figure this out, okay? So that is the last thing that you need to learn for this, and I realize that that one might be the most confusing. So if you have questions, please don't hesitate to reach out for some help. You know, I'm always more than happy to help you guys. And here is the last slide. It's just the concept summary for this section. Have a fantastic day.